Next up, we have Diego, who is a part of the OFA TWG, but he's also a member of the IBTA TWG, and he's going to give us an update on the advances of RoCE.
So I'm going to provide an update on behalf of the IBTA on something that we've been calling RoCEv2. And as a way of introduction, I'm going to start talking about what we used to call RoCE, and in the context of this conversation is going to be the RoCEv1. Some time ago, we noticed at the IBTA that there was interest and market justification for creating a version of RDMA that would run on Ethernet fabrics. And we looked at the InfiniBand specification and the way it's so cleanly layered, and recognized that by just simply replacing the layer 2 in InfiniBand and the associated management infrastructure that was InfiniBand fabric specific, and putting Ethernet instead, we kind of very simply achieved the goal of having the exact same RDMA services and same RDMA semantics for Ethernet networks. So you could take an application that was coded to our OFA verbs and have it seamlessly run and attain the value proposition of InfiniBand RDMA, regardless of whether the underlying fabric was the canonical InfiniBand top to bottom or the InfiniBand transport protocol running on Ethernet. And this slide pretty much summarizes all that there is to RoCEv1. We took the InfiniBand packet as defined in year 2000 that is shown at the top of this slide. We stripped away the layer 2 aspects of that packet, the layer 2 header in InfiniBand, the so-called LRH, and its associated cyclic redundancy check, the VCRC. And we put an Ethernet layer 2 header instead with its frame checksum, and off we go. That is, in a few words, what RoCEv1 is all about. We started this work in May of 2009 when the IBTA formed the RoCE working group. The working group is called the IBXOE working group within the IBTA. A couple months after that, we made available a prototype that was delivering on the promise of InfiniBand RDMA on top of Ethernet. There was a little bit of discussion in the industry and a nice white paper that we managed to put together for the Hot Interconnects conference in 2009, where people from different areas in the I/O industry came to discuss the issue at hand and kind of concluded that RoCE was a reasonable thing to do. It took a couple months until we had a ratified standard by the IBTA, and soon thereafter we got this included upstream in Linux, and since then it's been an available standard with products available on that space. By the way, the RoCE annex that I'm showing a picture of its cover here, it's about 15 pages long, which is in a way a testament to how cleanly layered the InfiniBand specification is, which makes this so simple and straightforward. Now, RoCEv1, as defined, is a layer 2 protocol. As we have seen in the previous slide, there's a Ethernet layer 2 header immediately followed by the InfiniBand GRH. So from the perspective of an Ethernet network, it is a layer 2 protocol, even though it includes an InfiniBand layer 3 header. And that means that within an Ethernet networking infrastructure, RoCE can run within a single Ethernet layer 2 domain. Of course, people have, during the past few years, created several techniques, standards and non-standard, to scale up their layer 2 domains, creating bigger Ethernet layer 2 fabrics where you can run RoCE as defined. And Ethernet layer 2 fabrics go all the way from single racks, typically a couple tens, maybe 40, all the way up to 80 maybe nodes, to much bigger deployments where people aggregate racks using either flat layer 2 topologies or more evolved techniques that encapsulate those layer 2s and create the illusion of a single layer 2 domain with techniques such as trill, provider bridges, provider backbone bridges, and newer overlay networks that allow to do that. But in this context, and RoCEv2 as defined is limited to this single Ethernet layer 2 domain. And it's not much different than what FCOE is. FCOE was also defined at pretty much the same time. Back then, there was a vision of people maybe moving their data centers into bigger layer 2s. But time went by. This world is never static. And people do not always resort to a layer 2 when they have to deploy the data centers. There's a very common class of data centers where people continue to make massive use of layer 3 IP layer 3 technology. In this drawing, I'm showing one example that seems to be very popular, but it's in no way, our work is in no way limited to this. In this case, we have a bunch of racks. Each one of these racks is a layer 2 domain, but the connection of these racks is done by virtue of layer 3 equipment. And if you want to do RDMA within a rack, then you can use RoCE because, as we said, it's a layer 2 protocol. But if you want to go across racks, you need to go through a layer 3 IP device, and RoCE doesn't do that. And people that want to make use and take advantage of RDMA in this context don't want to be limited to do RDMA within their single rack. So that's where the need for IP routable RoCE arises. Now, when we look at the problem and at the RoCE spec in particular and how we do RDMA, we easily identify that the request is not so hard to satisfy. That in a similar way to what we have done before, when we created RoCE, starting with InfiniBand, we can in a quite straightforward way create a new version of RoCE that does exactly this as required. And the idea is to replace the existing layer 3 in the RoCE protocol that is currently InfiniBand's layer 3 by the ubiquitous IP layer 3 and the UDP wrapper that I'll soon get into more details about. So basically what we set to ourselves as a goal is to create a RoCEv2 that can be used in the context of the deployment that we have just shown, where the focus continues to be a data center environment. We're not precluding or a priori disqualifying other applications, but we're focused on the type of environment that we have always been historically focused, which is a data center. But one where layer 3 technology is being used and the layer 3 devices that need to be crossed in order to get from one RDMA end node to the other. So as I just described, what we're doing is replacing the InfiniBand GRH with an IP header followed by a UDP header So whereas previously a RoCE packet was univocally identified through the ether type value in the Ethernet layer 2 header, now the ether type value in the layer 2 header indicates that the packet is just an IP packet. The protocol number in the IP header indicates that the packet is a UDP datagram, and it is using the common practice of identifying protocols or applications on top of UDP through a well-known destination port number in the UDP header that we identify the packet as being a RoCEv2. So the concept of very straightforward and stateless identification of a packet as being a RoCEv2 is completely preserved. This follows common practices these days in the IP world. Several protocols are in the process of being deployed or stages of being defined that take a very similar approach. In this spirit is that we're defining RoCEv2, expecting it also to be quite similar in terms of the scope of the work, and the complexity as if it was the definition of RoCEv1 compared with InfiniBand. In other words, something quite simple and straightforward. Few highlights, maybe repeating a little bit myself. It's a completely contained change. We're just doing a clean replacement of the layer 3 in the previous protocol. The strict layering is preserved. We don't want to mess with that clean architecture that we have. All of these changes that end up happening in the format of the packet end up being completely contained within the implementation of the RDMA layer. I'm sure people in this room are familiar with the semantics of InfiniBand RDMA that are message-based. So InfiniBand packets or RoCE packets or RoCEv2 packets never get to be seen above the API. The API is message-based. So all these minor changes or contained changes that we're doing to the packet are even happening within the implementation. The applications or ULPs that make use of it don't see them. So it is transparent to the applications because, as I said, the packets are not seen, but also because the APIs, as they exist today, are IP-based no matter what. The APIs, even for InfiniBand network, when there is no Ethernet, are IP-based through the RDMA-CM. So an application that is written today using RDMA-CM APIs can run seamlessly over any of the three alternatives that I shown: InfiniBand, RoCEv1, or RoCEv2. But also a very important aspect of this approach is that it makes it absolutely transparent to the underlying networking infrastructure. Because we're now creating UDP packets that are among the two most common type of packets that switch and router equipment are used to see. So by generating these RDMA on top of UDP packets, we're effectively riding on the mainstream data plane of the existing networking technology. We can therefore leverage all of the common practices that are prevalent in networks in data centers today. And by way of example, I'm mentioning here ACLs, for example, in the context of firewalling or monitoring or metering. We can use IGMP snooping for optimizing multicast distribution of InfiniBand RoCEv2 traffic. We can use our existing network monitoring tools because all we need to do is to tune them to the UDP port number that we're using for RoCEv2. The IBTA initiated this work close to the end of last year, in November of 2013. We were invited to give a presentation to the IETF in the November 2013 meeting in Vancouver, where we disclosed the fact that the IBTA was working on a IP routable version of RoCE, and this was very well received by the IETF community, which is a very important thing for us. The IBXOE working group that had defined the RoCE v1 spec was reactivated, and we started working in December of last year. And we have an initial draft of the RoCE v2 spec that is under review by the working group. And we expect to follow on with wider audience reviews and eventually publication of the standard soon. Any questions?
Do you believe in the lossless L2 network?
I'll repeat the question for those that couldn't hear it. The question was whether I believe or not in the lossless L2 network. My answer is yes. From the IBTA standpoint, the InfiniBand network is lossless. The RoCE network is lossless, and RoCE v2 for the time being continues to make the same assumption. We understand that in the worldwide internet, that may not be an acceptable assumption. But as I was saying before, we're focusing on data center environments where things are homogeneously managed, and the people can resort to deploy lossless techniques for RDMA traffic. I personally have seen even interesting analysis that show that lossless behavior may be even helpful for the legacy non-RDMA traffic, such as TCP and UDP, but that's a different discussion. Yes?
So is the spec specifying IPv4, IPv6, as well as common protocols, like VXLAN?
Yes, well, the spec explicitly covers both IPv4 and IPv6. Overlay protocols are orthogonal to the spec because they just encapsulate the complete thing. So the spec is doing nothing to preclude that, nothing to prevent it. But at this point, we haven't seen anything that we need to do specifically in the spec to support it, in the same way that you don't need anything in the TCP RFC to support the VXLAN encapsulation of TCP packets. Yes?
I have a question also about lossless communication and RoCE v1. Communication is lossless because...
Could you please speak up?
I have a question about the lossless nature of RoCE communication. So, to make communication lossless, false mechanism is used, that the false packet itself is layer 2. How will that packet expected to cross the router?
No, the pause that you're referring to is a link layer flow control mechanism, that it's point-to-point between devices. So it never goes across routers. So pause is on a link-by-link basis. And this continues to be the case here. Any further questions? Yes.
So you mentioned UDP because of its ubiquitous support. Did you consider other protocols beyond UDP, like SCTP or others? Or is there a reason for UDP?
Okay, so I myself did consider many options. We at the working group only discussed a UDP approach, and the consensus was that it was the most reasonable thing to do, that it was a reasonable thing to do. That's pretty much the preferred approach taken by many other protocols that are running in an IP network. It's also kind of the advised method by the IETF. Yes, as with most technical problems, there are multiple possible solutions. We believe that UDP is the best one. Specifically about SCTP, we don't need the reliability, and we already implement the reliability in the InfiniBand Transport Protocol. Yes.
Can be still made routable without a unity header as well? Was it considered?
Technically, yes. You could have achieved routable support without the UDP header, and then you would have had to get a protocol number that identifies the packet as being RoCE. That may not have been acceptable to the IETF. But yeah, what you just implied makes a lot of sense technically from some perspectives. On the other hand, even if we were to get the buy-in from the IETF into getting equivalent status to a TCP and UDP, then that would have required the networking equipment that routed this packet to become aware of this third protocol. I mean, not the third, there are other things. And that would have made it more required, more involved interaction with the people that now can stay completely agnostic to the fact that they're delivering RDMA traffic. It kind of makes things very clean to be running on UDP. Yes?
The next hop IP address, I assume it's registered with the Q pair, and if it were to change, is that dynamic? What happens there?
The next hop
Yeah,
IP
how do you
address?
obtain the routing information from the source? Can the route change over the IP network for the life of the Q pair?
The route can change. The route could change, and that is orthogonal to the end node. If the end node changes its name, is that what you're asking? If the end node is no longer referred to by its old IP address, but it gets a new one, was that the question?
No, just looking for IP topology changes where the packets can be rerouted.
Yeah, I think, right. So I think that as long as that doesn't happen too frequently, then the transport protocol in InfiniBand is going to be able to deal with the consequences of eventual, occasional loss or misordering as a result of such a change. Yes.
I have a question about interoperability. If there are RoCEv2 interfaces and RoCEv1 interfaces in the same network, will these be able to communicate with each other?
That's an interesting point that we haven't yet closed on at the working group. A RoCEv1 implementation cannot talk RoCEv2. It just speaks a different wire format. So the only way by which this could be if a RoCEv2 would speak RoCEv1. Yes.
You're not copying the version number anywhere from 0 to 1 with this V2.
There is no version number. RoCEv2 is a marketing name. It's not like there's a version number in the protocol. Okay, thank you.